Hello everyone, this is Arun. Today I'll be covering the week 5 of the session. This is the compensation class which was cancelled last week. So, since on Monday I covered the week 4 part, today I will be covering the part of the week 5. So, in the week 4, what we saw was what is principal component analysis, and we saw an example on how to solve manually, like to determine the first principal component. Then I also demonstrated how to do a feature space plot in QGIS. Then we saw what are the band ratios and what are the different indices. So we saw NDVI, NDWI, NDBI, and how to do that in QGIS also. And then we saw what is image classification, what are the different levels of classification, and we had different scenarios, which will determine the level of classification that you would like to do for your study area. And then there is supervised classification, unsupervised classification. In that, once we get our classified image, we do the accuracy assessment on that image, and then we check for the accuracy of the classification. And we also worked out one example problem on the accuracy assessment. So in today's session, we'll be seeing some problems related to photogrammetry. So I'll be deriving some of the formulas, and I'll be I'll work out some of the problems which are commonly asked in the courseworks as well as in competitive examinations. And I'll demonstrate the histogram equalization, which was part of the third week lecture, since it had an error. So I'll be demonstrating it today. And I will also demonstrate how to do unsupervised classification in QGIS. And after any classification, we can notice that after some like 1 decade, there will be some growth in the urban area, or some of the agriculture area might have been converted to some other land use class. So we will be looking at what is the change that is happening over time, and we do that by the change detection method. So I will demonstrate how to do a change detection if we have two different land use classification from different time period. And towards the final part, I will briefly introduce the microwave remote sensing. So that is the agenda for today's session. So I will share my other screen now so that we can work out on the problems. So I have around 6 problems with me, and in addition to that, I will so I have around 6 problems with me, which are very commonly asked. Before going into the problems, I'll be showing some of the derivations, how these concepts are being used. So what we are going to talk about here is only the vertical aerial photogrammetry. So from the lectures, you would have noticed that there are two types. So one is the oblique angle, and another one is the tilted. Then the final one is the vertical method. These are the different modes of acquiring photographs, and differences between them is also noted in that in the video lectures. So what we will be doing here is we will be dealing only with the vertical aerial photogrammetry. So before going into the vertical aerial photogrammetry, uh, just to understand the concept of how the photograph is being captured, so I'm going to draw some image to explain that. So these are the three different planes. So the first plane is the negative plate of camera, and somewhere in between we have our focal length. So let's say this point O is at a distance f from the negative plate, where O is the optical center. And since this is the negative plate, so imagine that you have a same kind of a plate in front of the camera, which is on the right side of the optical center. So we can name that as the positive plate. So this is a imaginary, and this is also located at the same distance from the central point, same distance, focal length f. And the point which you are seeing, that red color point, that is the principal point. And the final plane that you are seeing at the towards the right hand side, so that is the object that you want to capture. The red dotted line is the axis of the camera, and the point on the object plane, that is called as the principal point of object. So now we are assuming that this object is at a distance capital D from the optical center of the photo, optical center of the camera. So that distance is capital D. So this is when we are capturing something in the horizontal position. So now what we can do is, since it is a vertical photogrammetry, we are going to rotate this 180 degree. So this is in case of horizontal. Now if we want to do the same thing for vertical, so our optical center is somewhere located here. So this distance is F, and again this distance is also F, and the principal point of the object is located at a distance D from the optical center. So this distance will be D. Now for all our further uh, discussions, what we will be using is from this point alone. So the dotted line which I am drawing. So we will consider all our discussions with respect to the optical center of the imaging system. So here it is your negative plate, this is your positive plate, and this is your object plate. Now let's go into the vertical aerial photogrammetry. So in any photograph, the first thing that we need is the scale. So we are capturing the ground, and some distance on the ground will be equal to a some distance in the photograph. That is the scale of the photograph. So first thing is the scale of the photograph. So to understand that, uh, so all the objects are referenced with respect to the mean sea level. So I have drawn the mean sea level first, and let's say our ground level is somewhere here. So this is the ground level, and the difference between these two levels is small h. And let's say our imaging system is at a height capital H above the ground surface, above the mean sea level. So this is our height at which the image is being captured. So this height, the difference from the ground level to the imaging system will be capital H minus small h. And we know that our positive plate is at distance small f from the image optical center. So this is your optical center and this is your small f. Now we are going to capture 2 points. So let's say this is capital A and this is capital A naught. So they are at the same vertical line. Now when you are capturing a photograph, so this is the perpendicular point from the center of from the optical center, and we are going to capture the point A. And we are also going to capture the point A naught. So the points where it is intersecting, that's where our point A as well as so so we represent the image coordinates as small letters. This is A and this is A naught. So this is how it will appear on the photograph. So now we need to know the scale. So what we are going to do, we are going to make use of the principle of similar triangle. So if I say that, so let's say this is the x direction, this is the y direction, and the vertical is the z direction. So this point A has a capital X comma capital Y coordinate. So and this has a capital X naught comma capital Y naught as a coordinate. So the same points will have the coordinates small x comma small y in the photograph and x naught comma y naught in the photograph. So now consider, so I will use the pink color to highlight the triangles. So the pink color highlighted is the first triangle, and then the dotted line is the uh, bigger triangle. Let's say this is at a distance of x, and this distance is x naught. So we can write x small x by capital X is equal to x naught by capital X, which is equal to, so these are horizontal dimension, it should be equal to the vertical height of the triangle. So this is small f from the first triangle, and this is h minus h from the second triangle. So this is the scale of the photograph. Now there is another scale. This is with respect to the ground elevation. Suppose if you are expressing your scale with respect to the datum, that is your MSL, that is called as your datum scale. So datum scale is nothing but so your coordinates will be equal to f by h only. It will not be h minus h. You should consider the bigger triangle. So that is your datum scale. And suppose if your ground elevation is not flat but it is undulating, so in that case what we can do is we can represent a average scale. So that is nothing but f divided by h minus, instead of elevation at the point, we will take the average elevation of the area. So that is your average scale. So I will write down the terminologies. So x and y. So here it is second coordinate. So this is with respect to the scale of the photograph. Now once you know the points, once you know the scale, so you can determine the scale, and you will know the photograph coordinates. So x comma y. So by using this two, you can get your ground coordinates. So you can get capital X as, and capital Y as. So once you determine the ground coordinates, suppose if you want to find out the horizontal distance between 2 points, so you can use the distance formula. So you need to determine what is XA, what is YA. This is from the by scaling up, and you need to determine what is XB and what is YB. Then you can determine your horizontal distance. So that is represented by DH is equal to. So it's your normal distance formula. And suppose if the terrain is highly undulating and you want to find out the incline distance. So let's say, let me just, suppose let's say this is point A, then this is point B. So by first method, you will get what is the horizontal distance between these 2 points. This is DH. But if you want to know what is the inclined distance, so then you need a third coordinate, that is your elevation. So di is nothing but your inclined distance. So same distance formula, just your elevation will get added up.